Alright, dear friends, today we are going to dive into identifying functions and their derivatives from graphs. Here is a three graphs, but they are not labeled. Our task is to figure out which graph represents the function. F is first derivative f prime and its second derivative f double prime. Let us come to the first derivative test. We know the first derivative represents the rate of change of the function. If the function is increasing, then the first derivative is positive. If the function is decreasing, then the first derivative is negative. And if the function has stationary point or critical point or turning point, means there is neither increasedness nor decreasedness, then the slope is zero, means the first derivative is zero. We can see it visually. Let us divide the function in the pieces where we can find the increasedness and decreasedness of the function. In the first part, the function is increasing, so the first derivative is positive. In the second part, the function is decreasing, so first derivative is negative. In the third part, function is increasing, so the first derivative is positive. Please note that at this point, the first derivative is 0. And also at this point, the first derivative is 0 because in this point, the tangent is parallel to x-axis. Let us come for the second derivative test. The second derivative represents the rate of change in the velocity. If the function is concave up, then the second derivative is positive. If the function is concave down, then the second derivative is negative. If there is no concaveness, then the second derivative is 0. So in this graph, let us divide it into a pieces where we can see the concaveness either upwards or downwards. We can see that in the first part, the function is concave up. So in this region, the second derivative is positive. In the second part, the function is concave down. So in this region, the second derivative is negative. In the third part, the function is concave up. So in this region, the second derivative is positive. In the fourth part, the function is concave down. So in this region, the second derivative is negative. Please note that at the points where the function is neither concave up nor concave down, means at a points where there is a transition between concave up and concave down. For example, in this curve, there are three such points: point A, point B, and point C. In such cases, the second derivative is 0. We call it the point of inflection. In a curve where the first derivative is positive and second derivative is positive, it looks like that. The function is represented by red curve, the first derivative by green, and the second derivative by blue. Similarly, the curve where the first derivative is positive and second derivative is negative looks like that. The function is represented by red curve, the first derivative by green line, and second derivative by. Similarly, for a function where the first derivative is negative and second derivative is positive looks like this, in which the function is represented by red curve, the first derivative is by green line, and second derivative is by blue line. So for a curve where the first derivative is negative and second derivative is also negative looks like this, in which the function is represented by red curve, the first derivative is by green line, and the second derivative is by blue line. This kind of information help us to identify the shape of a graph. Now we have a graph of three functions, but they are not labeled. And now our task is to figure out which graph is which, means which is a function and which is a first derivative and which is a second derivative. So let us analyze the graph one by one. So let us start by the red curve. We can see that the slope of a rate function is 0 around the interval 2 to 2.5 and the interval 3.5 to 4. So the first derivative of the rate curve is 0 within these two intervals. So let us write in this graph where the rate curve has 0 slope. Similarly, let us try for the second derivative. We can see that in the rate curve, the point of inflection lies around the interval 1 to 1.5 and around the interval 3 to 3.5. So we write that information in this table. For the rate curve, the second derivative has 0 in the interval 1 to 1.5 and 3 to 3.5. Now we will do the similar analysis for green curve. For the green curve, we can see that it intersects x-axis at some points in the interval 2 to 2.5 and 3.5 to 4. So we write that information in the table. For the green curve, the function has zeros at some point in the interval 2 to 2.5 and 3.5 to 4. Similarly, for the green curve, the slope, the first derivative is 0 at some points in the interval 1 to 1.5 and 3 to 3.5. So we put this information in the table where the first derivative is 0 at some point in the interval 1 to 1.5 and 3 to 3.5. Similarly, we analyze the concaveness of the green curve. We can see that the point of inflection lies at some point in the interval 2 to 2.5. So we write that in the table. The second derivative is 0 at some point in the interval 2 to 2.5. Now we analyze the blue curve. We can see that the blue curve intersects x-axis at some point in the interval 1 to 1.5 and 3 to 3.5. So we write that information in the table where the blue curve has functional value 0 at some point within these intervals. For the blue curve, the slope is 0 at some point in the interval 2 to 2.5. So we write that information in the table. It shows that the blue curve has 0 derivative at some point in the interval 2 to 2.5. And for the second derivative test for the blue curve, we can see that there is a point of inflection at some point in the interval 0.5 to 1. So we write that information in the table. It shows that the blue curve has point of inflection around some point in the interval 0.5 to 1. Here we can see that the derivative of red curve is green curve because first derivative of red curve and function of green curve are same at test points in the interval. That is why we can claim that the derivative of red curve is the green curve. Similarly, we can see that the second derivative of red curve is the blue curve because the point where the value of the second derivative of red curve is 0 is the same point where the functional value of the blue curve are 0. So we can claim that the second derivative of red curve is blue curve. Let us test more precisely. We can see that the first derivative of green curve is the blue curve because at our test point where the first derivative of green curve is 0 are the same points where the functional value of the blue curve is 0. So with this analysis, we claim that the points where the derivative of red function is 0 are the same points where the green function's functional value are 0. The points where the second derivative of red curve are 0 are the same points where the functional value of the blue curve are 0. Also, the first derivative of green curve and the functional value of blue curves are 0. That is why in this graph, the first function means the function is red curve, the first derivative is green curve, and the second derivative is blue curve. With this, we would like to conclude here. So thank you for watching for this video.